Good morning, everyone, and welcome to our NASA briefing on some exciting news we have on one of our Mars missions. Before we get into it, I want to welcome our presenters who are going to be participating in this briefing today. First, we have Nikki Fox. She's the Associate Administrator for the Science Mission here at NASA. On the phone, we have Katie Stack Morgan, the Perseverance Project scientist. She's going to present via phone. We also have Professor Joel Hurwitz, Perseverance scientist and lead author of the paper that was just released today. Very exciting. He's on the phone as well. And also we have Lindsay Hayes. She's the senior Mars scientist. She's with us here in person. As well as we have our new associate administrator, who, if you have any questions, you will ask questions of him as well. Amit, who I'm grateful he's accepted the post as the top lead career employee. I formerly worked at on the mission for Artemis, which is, we're going to talk about that a little bit later. But for today's press conference, for the last 30 years, NASA has been exploring Mars. And in that exploration, we're looking for signs of life, we're looking for water, but 30 years of exploration. And in the past, we thought we found signs of life. And when we did that, we put it out to the scientific community. And the scientific community would come back and say, well listen, there's different explanations for what you think was life. It actually was created by something else. And that's been the history, the partnership that NASA has with its discoveries and the scientific community that will, in essence, pressure test what we think we've found. So we're talking about Perseverance. This was a mission sent to Mars under President Trump's first presidency. And a year ago, we found a sample, and it was, again, we're exploring in places where there were rivers and where there were lakes. And much as on Earth, we think that that's where we'd see signs of ancient life on Mars. And so a year ago, we thought we found what we believe to be signs of microbial life on the Mars surface. And so we put it out to our scientific friends to pressure test it, to analyze it, and go, did we get this right? Do we think this is signs of ancient life on Mars? And after a year of review, they've come back and they said, listen, we can't find another explanation. So this very well could be the clearest sign of life that we've ever found on Mars, which is incredibly exciting. Again, we're gonna break that down for all of you with our lead scientists here at NASA, those who have been involved. Dr. Hurwitz, Professor Hurwitz, wrote the paper that was released today, so we want to hear from him as well. But I would be remiss if I didn't talk about what we're actually doing here at NASA, which is human flight exploration. Many of you have heard about our Artemis program. At the first part of next year, we're going to send 4 astronauts back to the moon, but we're going to just go around the moon. We're not going to land in Artemis 2, which is coming early next year. But about a year and a half after that, we're going to do Artemis 3. We're going back to the moon. And this time, we are going to stay for a longer period of time at the start, but we want a long-term presence of life on the moon led by America. And what's important with this mission is what we learn on this mission to the moon is going to help us to actually put American boots on Mars. And it's an exciting time. And again, we have great science around it. We're pushing our partners. We're pushing NASA. We're in a second space race right now. The Chinese want to get back to the moon before us. That's not going to happen. America has led in space in the past, and we are going to continue to lead in space in the future. And again, this discovery today, I hope makes everyone excited about the future missions that we're going to have and the exploration we're going to do and the science we're going to develop to make sure we can send Americans, mankind throughout the universe. And so, but we do want to lean into this exciting news that we have today. And to give us more, I'm going to turn it over to Nikki Fox, who is the Associate Administrator for our science mission. Nikki.
Thank you so much. Thank you. Yes, it really is an exciting day today. NASA, what we do is we study the seemingly impossible. That's what we do every day at NASA Science. And NASA Science is undisputably the global authority in the search for life beyond our home planet. And so today we are going to talk to you about this amazing, exciting discovery. And I also want to make sure that we put context around it. And you see like how it fits into our search for life in the universe. Our galaxy is 100 billion light years across. And within 10 light years of Earth, there are at least 400 known planets. And that means there is a possibility, some would even say a probability, of life beyond Earth, including maybe even complex intelligent life. And today, we are really showing you how we are kind of one step closer to answering humanity's one of their most profound questions, and that is, are we truly alone in the universe? So if I could have the first image, please, that would be great. So last July, as Secretary Duffy eloquently described, NASA's Perseverance rover found a leopard-spotted rock at Mars. And scientists immediately knew, it was interesting, we hadn't seen anything like that before on Mars. And we talked about it last summer. The moment we found it, we put out the images for everybody to see and everybody to share in the joy of NASA science. And, you know, today, we're really here celebrating that incredible hard work of the science team as they literally tried to prove it wasn't interesting. Maybe it's just something else. Maybe it's not, you know, the key result that we've been waiting for. And so they've done the analysis on these leopard spots, and we think they are potentially made by some sort of ancient life. This finding by our incredible Perseverance rover is the closest we've actually come to discovering ancient life on Mars. And if you can't tell, we're really excited about that. But, you know, I want to put it into context. It's a signature. It's a sort of leftover sign. It's not life itself. And it certainly could have been from ancient life, and that would have been something that was there billions of years ago, nothing that's current there. And, you know, it could certainly, as we say, be made by ancient life. And what that means is we look at everything we know about life on Earth. And this is the kind of signature that we would see that was made by something biological. In this case, it's kind of the equivalent of seeing like leftover fossils, you know, leftovers from a meal. And maybe that meal's been excreted by a microbe. And that's what we're seeing in this sample. And, you know, again, as Secretary Duffy said, we don't know for sure that's what it is, and we won't stop after this first analysis. This certainly is not the final answer. But we have this first result, and we're sharing it with you, the world, and we are asking you to look and give you our analyses also. And that's what we do in NASA science. This is, you know, how we find our information. It's part of that long journey. We ask a question, we design a mission that can actually go and address that question. We develop the technology, we build the hardware, we launch it into space. It takes the data, it brings back the information that we need here, we analyze it, and we come up with answers to those really, really tough questions. We've actually been studying Mars with, even as early as 60 years ago when we sent our first missions there to take pictures of Mars and tell us really that's quite an interesting place and we really do want to send humans there. And so we've been doing this so we can understand the planet so we are ready to send our humans there. We certainly, as we look forward, we plan to send more missions to Mars in support of the Artemis program, which we're really proud of. And it will open the door for humans to study and better understand the red planet and perhaps even one day bring back Martian samples home for us to actually study here on Earth. And I want to underscore the point that NASA science discoveries do not just happen at random. They are the rewarding results from meticulous, long-term strategic planning. We send these missions to really address these incredible questions. And each new discovery helps us just, kind of drive what research is coming next. What missions do we want to design next so we can kind of take that full bench of tools with us to solve the problems of how best to explore our solar system. First with robotic missions and then with humans. And before I pass it on to my colleagues who are going to tell you all about the details of this incredible finding, I just want to talk a little bit more about how NASA searches for life. And there's so much happening that I am incredibly excited about. We have Europa Clipper that is on its way to explore an icy moon of Jupiter to investigate whether the subsurface ocean underneath that icy crust has the potential to support life. After that, we'll launch Dragonfly, which has been deemed the most exciting science space mission of your lifetime. And it's a drone. It's the size of an SUV, and it's going to be humanity's first airborne science mission to another world. Dragonfly will explore the amazing world of Saturn's moon Titan, which is the only place in our solar system where that have lakes of liquid on the surface. And with Dragonfly, it's going to let us understand the prebiotic chemistry that predominated Earth here before the origin of life. And the other thing we're looking for all over the universe is potentially habitable worlds. 30 years ago, we first discovered an exoplanet around another star system, and today we know of thousands of them. This has changed the very way that we look at our night sky. We know that there is, on average, a planet for every star in the sky. And as I've been saying, each new mission is specifically designed based on all of the knowledge that we've gained so far. And in this case, the knowledge is allowing us to lean forward to study a concept mission that is supported in the president's budget called Habitable Worlds Observatory. And that will allow us to search for habitable worlds and for signs of life around 100 of our nearest stars. Super, super exciting. Mm-hmm. From its vantage point in deep space, it will observe a variety of critical targets for us to go and explore, for us to sort of put our fleet of telescopes staring at those, including our amazing James Webb Space Telescope, and of course our upcoming flagship mission that we launched in 2027, the Nancy Grace Roman Space Telescope. Super excited, yay Roman. The Habitable Worlds Observatory insights could help keep astronauts and human infrastructure safe in space, and it will be the most powerful telescope NASA has ever launched, maintaining Americans' leadership in space, which is so important. But for now, back to the present and back to Mars. And so I am delighted to turn it over to Dr. Katie Stack-Morgan to tell us more about Perseverance's work on Mars, and she's joining us by phone. Take it away, Katie.
Thank you so much, Nikki. The discovery of a potential biosignature or a feature or signature that could be consistent with biological processes, but that requires further work and study to confirm a biological origin is something that we're sharing with you all today that grows from years of hard work, dedication, and collaboration between over 1,000 scientists and engineers here at the Jet Propulsion Laboratory and our partner institutions around the country and internationally. A discovery like this comes from years of strategic planning and science analysis from both the rover team as well as the Mars community, as we went from the development of the Mars 2020 mission as a concept in response to the priorities of the Planetary Decadal Survey, to the landing site selection, and now to the daily operations of the rover that provide us such a fantastic data set that we're going to share with you today. If we could bring up the first image here, I'll be providing some overall geologic context for the discovery of these leopard spot features. The Perseverance rover landed in Jezero crater in 2021, and this site was selected as the result of a multi-year community effort because we decided that this site was truly the best place to accomplish the Mars 2020 mission goals of seeking signs of ancient life on Mars and putting together a collection of rocks for possible return to Earth in the future. Jezero was selected because it's in a location amongst the most ancient terrains on Mars, exposing some of the oldest rocks anywhere in the solar system. And these really ancient rocks provide us a window into a period of time that's not particularly well represented on our own planet Earth, but it's a time when life was emergent on Earth and could have been on Mars as well. Jezero is also indisputably the site of an ancient lake, which we know because we have two river valleys entering into the crater and a river valley exiting the crater through which water flowed out of the crater. During the first 4 years of the mission, Perseverance explored three main geological terrains within the crater. The rover landed on the crater floor, which was a sequence of igneous rocks, including lava flows and igneous cumulus, that had a number of interactions with water and preserved probably micro-environments that were likely habitable. The rover then transitioned to the western fan. It's a sequence of sedimentary rocks whose sediments were transported from ancient terrains out of the crater into the crater in a relatively long-lived and stable lake, delta, and river setting. The rover then transitioned to what we call the margin unit. This was a thick sequence of igneous rocks that really distinguished themselves by strong orbiter spectroscopic signals of the minerals olivine and carbonate. After the margin unit exploration, the rover had a chance to traverse into the Retva Vallis, which is the main feeder river valley that once fed the ancient lake that was present in Jezero. And this river valley, more than 3.5 billion years ago, this valley would have been filled with rushing rivers carrying mud, sand, and gravel from outside the crater into the lake inside the crater. This kind of energetic setting was probably punctuated by periods of calm when water would have backed up, creating a relatively low-energy lake environment where deposition by settling from suspension could have occurred. Eventually, though, this water dried up, the lakes and rivers dried up, and the Bright Angel outcrop was revealed. And this outcrop records for us a potential habitable environment that we can study and the rover can explore on the surface of Mars today. If we can bring up the next slide, please, we can see Bright Angel through the eyes of Perseverance. It's a distinct light-toned outcrop, and its current extent and relief has been exposed to us through billions of years of wind, erosion, and thermal cycling. The rover spent several months exploring this area, ultimately pushing to the edge, the northern edge of the channel, where the Bright Angel formation met the margin unit. And it's here at the contact, this edge of the river valley, that the rover explored a special target called Chayava Falls. If we move to the next image, please. The Chayava Falls rock and those around it show very thin layers. They're often red to tan in color, and they're very fine grained. So the sediment that makes them up is very, very small. This, coupled with the fact that these rocks occur in a river setting, really points to a sedimentary origin here, where we had deposition of these sediments in water. Here in this area, we also have some coarser-grained rocks, again suggesting that we had a transition from these more energetic river environments to the more calm lake environments. And while every outcrop on Mars has an interesting story to tell, in order to really understand what makes this particular outcrop so special, we have to get our noses to the outcrop, or in this case, the rover's arm, up close and personal to take a look at all the details of these rocks. So to tell us more about that, I'm going to pass it on now to Professor Joel Hurwitz, who is the lead author of the study that came out in Nature this week. Joel, over to you.
Thank you so much, Katie. If I can bring up the first view graph, what you're looking at here is a selfie that Perseverance took of itself in front of the Chayava Falls workspace in the Bright Angel Formation. And I show this image, one, to kind of provide a little bit of additional context and show that we collected a sample from this rock. You can see a hole in the rock where that sample core was collected. But also to make the point that we really used every scientific instrument available to us on the payload to investigate these rocks and really try to tell or paint as complete a picture as we can of what these rocks are made of, the environment they were deposited in, and how the interesting features that we see in them might have formed. So what I'm going to do now is I'm going to move to the next image, and we're going to zoom back up to the surface of the Chayava Falls rock. And this is the same image you were looking at before. And what I want to do with this image here is I just want to convey some of the excitement that we had when this image came down last summer. And what we saw in this rock were these layers of very fine-grained, rusty red mudstone that had in them these incredible features, these things that we took to calling poppy seeds, which are the sort of dark black spots in the rock, and leopard spots, which are these kind of ring-shaped features that have dark rims around them. These textural features told us that something really interesting had happened in these rocks. Some set of chemical reactions occurred at the time they were being deposited. And so we really wanted to understand what those reactions might have been. And one of the things we wanted to ask ourselves was, is it possible that organic matter might have played some role in the generation of these textural features? So we turned to our organic chemical detector, the Sherlock instrument, and trained it on this rock at the location of those two little black boxes that you see on the surface of the rock. And I'll switch to our next view graph. The data that we got back from the Sherlock instrument was fantastic. What you can see here is a set of spectra that are called Raman spectra. And there's a lot of information on these graphs, but the key thing to take note of is the fact that what we see in these spectra is something called a G-band, and that's pointed out on the image. The G-band for us is a smoking gun indicator for the presence of organic matter in this mud. And we see that G-band in the Chayava Falls target, and we actually see it in a couple of the other locations that we interrogated around the Bright Angel Formation. And this tells us that we had a rusty red mud that was deposited in the presence of organic matter. So the next question for us was there some reaction occurring between the mud and the organic matter to give rise to those interesting poppy seed and leopard spot textures that we were seeing? So we turned to the other instrument out on the end of the rover's arm called the Pixel instrument. And the results from that instrument are shown on my next slide. Here what you can see is the chemistry of the surface of this rock rendered in three colors, red, green, and blue. And the mixing between colors is telling us something about where elements are present together. What I'm showing you here is that the mud itself, which shows up in red in this color representation, is rich in iron. The things that are purple are rich in the elements iron and phosphorus, and that iron and phosphorus shows up in the poppy seeds and in the rims of those leopard spots. In the places where you can see sort of dull yellow to green tones, that's where iron and sulfur have been combined together in the cores of the leopard spots. And they have been combined into an iron and phosphorus-bearing mineral that we think is vivianite, and an iron and sulfur-bearing mineral that we think is a mineral called greigite. And what's exciting about these finds, this sort of combination of mud and organic matter that has reacted to produce these minerals and these textures, is that when we see features like this in sediment on Earth, these minerals are often the byproduct of microbial metabolisms that are consuming organic matter and making these minerals as a result of those reactions. But there are non-biological ways to make these features that we cannot completely rule out on the basis of the data that we collected with our rover payload. So what we need to do from here is to continue to do additional research in laboratory settings here on Earth, and ultimately bring the sample that we collected from this rock back home to Earth so that we can make the final determination for what process actually gave rise to these fantastic textures. So with that, I'm going to close out, and I'm going to turn it over to Dr. Lindsay Hayes for the next part of the program.
Thanks, Joel. So in order to wrap us up, I really want to highlight some context for the points that we've made here today. First, we are excited. We're excited to be announcing the publication of this peer-reviewed paper about these features from this about 350 billion-year-old rock on Mars, right? This is about the same time as we see some of the earliest fossils of life on Earth. And so these features are helping us to better understand the potential biological history of Mars. After our announcement last year, the peer-reviewed publication is the next step in the scientific process, and it allows NASA to make the data that we collected from this mission and the science team's interpretation of that data sort of available to the broader science community for further and wider study. This work to investigate the processes that are described here will continue, and hopefully, eventually, this will be followed by the delivery of these samples back to Earth, where they could be studied in terrestrial labs.
Additionally, I want to remind everyone that what we're describing here is a potential biosignature. That is a characteristic, element, molecule, substance, or feature that might have a biological origin but requires more data or further study before reaching a conclusion about the presence or absence of life. And then finally, as we have explored Mars, one of our main goals has been to determine if Mars was habitable in the past and whether or not life was ever present. This was part of the reason that we sent Perseverance to Jezero crater. And the findings that we talked about here, they weren't an inevitable result from this mission, right? They're the direct result of more than decades of work by tens of thousands of people with many different missions that were meticulously and strategically planned, payloads that were developed and missions that were executed capable to lead us to achieving this discovery. Our exploration themes, and I think there's a slide here,